These notes will cover the most important points of today's class. What I'm skipping is the recap, because if you want the recap for what came yesterday, you can watch the notes, the previous video that I made. And also in a second video, I will make a short video on the force, magnetic force between two wires. We did that in class today, but they really should be separate videos. So the main topic is making magnetic field. And quick recap just of Ampere's law, not of everything we did yesterday, but just of Ampere's law as a way to find the strength of this force. Ampere's law is similar to Gauss's law for electric fields. And if you remember, Gauss's law for electric fields basically boiled down to electric field times an area, which is another name for that is flux, equaled the charge enclosed by that area with a constant to make the units turn out right. And this area was a closed area, like a balloon or a closed cubic box, that kind of closed area. And this concept of electric field times area was flux, and this said if the flux through a closed area equaled the charge inside with a constant to make the units turn out. Well, Ampere's law is similar, but instead of an area, we look at a path. That's a difference. Same idea of closed, same idea of something inside that, and the same idea of this path being in space, and you have to imagine it. It's not physically like a wire. Just as with Gauss's law, it wasn't physically an actual box or balloon. You imagine the shape in Gauss's law, and you imagine the path with Ampere's law. So imagine any closed space, any closed path in space. And so for that path, I think I'll draw it in purple. Okay, here's a closed path in space. Okay, it's closed, it comes back on itself. Well, that creates an interior area. And within that area, there might be currents like coming at us, like here's a big I coming at us, I1, smaller I2 coming at us, and a medium-sized I3 going away from us. So if you look at this, there's a net current here coming at us, visually shown, because this I1 is big, this I2 is medium, and this I3 is medium. So the net here is there's more coming towards us than away. That would be what we call I enclosed. Now, if you remember for Gauss's law, officially it was an integral, but unofficially we had this concept. It seemed like all the time we actually used it, we were taking electric field and multiplying by an area. Same sort of thing here. So we're going to start with basically. We're not going to start with the full law with the integral, because you'd really almost never use that. But basically, if this total path length, the common symbol we use for that concept of total path length is L. If we call that L, and there's a magnetic field being created by these currents here, and it's round here, basically the idea is that instead of multiplying like electric field times area, you multiply magnetic field times L, the total path length. That will equal the current inside with a constant to make the units turn out. So here the I enclosed, the enclosed current would be the net of all three of these. Like consider there's a big plus I1, a small plus I2, and a medium negative I3 going into the page. That's what the I enclosed is. So that's basically Ampere's law. But of course, it's not always the case that this can work out as a simple multiplication. So you are supposed to understand what to do if in general. So if there are thetas involved and B is variable, if B is not a constant everywhere along the path. In other words, if you take a small segment of the path like this, okay, we'll call that delta L. And at that point along the path, the B points this way, B. Okay, well, of course, that creates an angle between them, theta. And it turns out that what matters, what you have to add up all along the path, is the part of B that points in the direction that is tangent to your path at any point. You add all that up, the part of B that's tangent to the path, add them all up around the entire closed loop. The sum of, let's see, how is the tangent part? Well, that's the cosine part. The sum of B cosine theta delta L. Add that all up, all around, and that's what this is. Okay? But this could vary continuously instead of in discrete parts, and so that means there's going to be an integral. So the official statement of Gauss's law is you add up all the parts of B that are tangent to the path continuously. So instead of saying the B cosine theta times the delta L, you write that as a dot product. The B, and remember what a dot product is, it's just this times that times the cosine of the angle between them. So that's what you're adding up. The part of B that's tangent to the path times the little infinitely short path length, and you add up them all, and you put a circle here to show you're going completely around the path once and coming back to where you started. That's the only thing that circle means. That will equal a constant times the total amount of current that is enclosed by that path. That's called Ampere's law, and it's a general, we consider a law of nature, absolutely true no matter what path shape you pick. This will be true. It looks like calculus, but you're never actually going to perform an integral. This is called a line integral. You're integrating along a line. It's not a surface integral like Gauss's law because it's not an area. You're integrating along a line, and this is what you're doing. But you're never actually going to do an actual integration, to do any calculus. So you have to know how to read this. It means take the part of B that's tangent to the path, multiply times a little bit of path length, add that all up over the whole path until you come back to where you started. And that will equal this. Okay, so that's what it means. All right, so that's a quick review of Ampere's law. Now we're actually going to use Ampere's law to figure out the magnetic field, like a formula for the magnetic field strength for certain geometries. And we'll start with the simplest possible geometry. So one wire of I makes B, makes a magnetic field. One wire of current makes a magnetic field. Okay, let's see what that would look like. Well, first, here's the I. We'll draw it as a dot. Okay, coming at us. The current is coming at us out of the page like this. Okay, and we already know what kind of field that makes. We draw circles, but what exactly does that mean? So we draw a dot here, and we want B at that dot. Okay, let's see. Right-hand rule 2, thumb is the current, fingers tell you counterclockwise in this case. You don't draw a circle here because we want the field at that point. You draw a vector, and vectors are always straight arrows. They're not curved. The circles with the arrows were just to help you draw actual vectors. So what that means is right at this point, the field must point up. Okay, that would be tangent to the circle that we learned to draw earlier. Okay, and what should the length of this arrow depend on? In other words, what makes B stronger or weaker? Well, of course, I. So B should depend on I. And what else should make, like if I wanted to make B weaker and I could do anything I wanted to, I could change the current, but what else could I do? I can move farther away, or I can move closer. So we want to express that with a letter. That's distance, and it's the distance from the wire of current to where what we care about. So the most natural letter for that is R in this case because we are looking at circles and that's the letter the AP uses, so we're going to use R. So B should depend on I and R. And we want to know that. What the strength of B, no arrow because we're just talking about strength, is a function of I and R, and that's what we'd like. How does it depend on it? And we're going to use Ampere's law to figure that out. So I'll write Ampere's law very quickly. B dot dl equals mu 0 I enclosed. But you're never actually going to use this as an integral. This is just a reminder of what it means. So there's the B, that's our dependent variable. And this is the L, the full path length, all the way around whatever path we choose. Mu 0 I enclosed. Okay, what path would you choose? Well, we'd like a path so we don't have to do any calculus. In other words, we'd like a path where the B is constant. So that means picking a path that's a circle. If we're outside one straight wire, and I really should put straight wire, one straight wire, because we'll look at non-straight wires soon. So one straight wire of I makes a B, and we know that this has a circular symmetry. B has the same strength everywhere along this circle, equidistant from the wire, and it also points tangent to the circle at every point. So there's no need to worry about a dot product. The angle between B and DL is 0 degrees, so there's no need to worry about a dot product. So we're just going to multiply these two things together. This is total length, path length. Okay, but we're not done because we want B as a function of I and R, the distance from the current. We've got B just fine, but you have to express path length as a function of R, all the way around here. And of course that's circumference, so that's 2 pi r. equals mu 0. And now here you put I enclosed. Since it's one straight wire, we're not adding up a bunch of different i's, some coming at you, some going away. It's just the single I, so that is the I. All right, we wanted b as a function of things, so we're going to solve this for b. And we get, I like to group the constants together, so I put the mu 0 over 2 pi together, and then group the things we can change, the variables like that. That's the formula for the magnetic field created by a single straight wire. This is not on the equation sheet, which I think is a big oversight. This is analogous to Coulomb's law for electric field. So I would put this on the equation sheet if I were making it, but they don't. So you either have to put this in your calculator or be able to derive it like this really, really quickly. Okay? And the basic idea is B times total path length is the constant times the enclosed current. This idea here will be different depending on your geometry. In this case, the symmetry is circular. It's not even spherical. This is a true circle. Everywhere along the circle, B has the same length. And it points, B has the same strength. And it points tangent to the circle at all places, so there's no need for any fancy dot products or cosines. Okay, so that's a really good thing to know. If you go into magnetism, you're going to want to memorize that as fast as you can and understand where it comes from. All right, next, that was our simplest possible case. The next case is the solenoid. And a solenoid is like this. It's like a slinky. It's multiple coils connect together, and I run current through this and it goes around in spirals. So to sketch a solenoid really quickly, it'd be something like this. All right, this is wire and we run current into it and coming up out of here. Okay, now when you draw it like this, there's no way to tell whether this is behind, like on the other side. I haven't drawn the pipe through it the way you did yesterday, so there's no way to tell. I'm just going to draw it like this, put the eyes like that, and say that the B inside goes like this. In fact, I think I can do this correctly. There we go. This will be better than the notes were today, because it is kind of showing what's in front and what's in the back. So that's the B. And then the B wraps around like this, wraps around like that. And I strongly recommend you look at an animation I uploaded from Penn State University, which is some three-dimensional computer-generated animations, and look at the one for the coil and for the stacked coils or the solenoid, and you get a really good idea of how this works, what the geometry looks like. Okay, what we would like to know is B. And we'd like to know B as a function of, I don't even know what it's going to be a function of, so I'm going to put what. And that's what we're going to try to figure out. We want an expression for B, for the magnetic field inside, the B inside the solenoid, because look, it's parallel, it's going to be uniform, it's very nicely behaved, we can control it by changing the current, and we'd like to know a formula for this B inside. We don't care about outside the solenoid. The interesting stuff happens inside, where the B is straight. We'd like a formula for that. We'd even like to see what it depends on. We are going to use Ampere's law again, which can seem really weird, and I remember I was surprised by this, how you could actually construct a closed loop that would answer the question here, and that's what we're going to do. When I first learned it, I was surprised and impressed. What we're going to do is take this, and I've got my slinky, okay, and imagine slicing it right through the middle. Slicing right through the middle of this with a piece of paper, and I'll draw it first down here. If you do that, you don't have coils anymore, you just get the little piece where you cut there and the piece where you cut there. So in other words, you have dots up here for the I, and you'll have X's down here. So let's draw that on a separate sheet of paper and see how we're going to use that to figure out a formula for the magnetic field inside. All right, so I sliced through the solenoid, and I have dots here, and that's I, and they become X's here. As the current comes around from the coil up and then goes down into the page and coils around underneath, and so it's like that. Okay, also I there. I is the current in the wire. That creates a magnetic field going through the middle like this, B. Eventually, at each end, the magnetic field curves. That's true at each end, it curves. And I really should draw more than one if I'm going to show that. Curves like that. Okay? But inside the solenoid, it looks like that. And I want an expression for that. Okay, so I need to draw an Amperian loop. It's called a closed loop that will take advantage of certain symmetries to make this easy to calculate so I don't have to use calculus. Right? So, well, I don't have to make the loop round or a circle. That's not a rule. It just has to be closed. So I'm going to make the side here inside nice and straight and exactly alongside or parallel to the B. Okay? All right? And so I won't need any thetas or any integration because B is constant inside and it points exactly tangent to this path here. So it's just B times this length, and I'm going to use the letter D for how long that side is. Then I do something really interesting, really cool. I make this loop really, really, really long. I can go miles and miles away, so essentially B is 0. B is 0 out here. Maybe I should switch colors. B equals 0 out here. B equals 0. So far away we can't measure it. So there will be no integration to do here. B times this side is 0. We're so far away, right? This would curve back and go the other way, but we're so far away, it's so weak we can't measure it. And then along here, we won't go into the details, but what happens is these sides in total cancel out. Because even if you get field coming at it one way here, and it'll be at an angle, it's almost perpendicular for most of this, and if it's a dot product, perpendicular means 0. Even if it's not perpendicular, you get the effect where it can come, certain lines will be pointing outward, other ones will be pointing inward in different directions, like this way, that way, and so the net effect is it cancels out. Plus, if we're very near to the center, the field out here will be almost 0 anyway. So I have 0 along these sides. So I only have one side, this side here, where I get any significant B times the length. All right, so let's go through the process of Ampere's law here. It was the integral, and you can think of writing the integral form first, but we'll skip right to BL equals mu 0 I enclosed. L was the total path length. Along this side, there's nothing significant, nor this, and here B is 0. If there is anything significant here, it cancels out with both of them. And the only significant B is here. So this becomes B inside times this part of the whole path, so that's the D. And that equals mu 0 times I enclosed. The I enclosed is where things now get interesting. Notice, I cannot just write I. This thing has a current of I going through a wire, but the wire is wrapped around in multiple coils, right? A whole bunch of coils like this. And look how many I've sliced. Look at the I enclosed. I've actually sliced and gotten 2 coils. So I would have to double I for this particular case. But should I put 2I? No, that'd be too specific to this picture. So in other words, the I enclosed is the I of one coil times the number of coils enclosed. And this is going to lead to something useful. Right now it seems like a lot of arbitrary things. Here I happen to enclose 2, but it's going to lead to something useful. So the current enclosed will be how many coils you've enclosed times the current in the wire. All right, so let's write this down and turn it into something useful. Okay, so B times D, that length that I took out of the middle there, equals mu 0 times the number of coils enclosed times the current of one coil I. Right now this is not useful, but remember we're trying to find an expression for B, so let's solve for B, which just means dividing both sides by D. And you'll see it works out best if we put it under this thing, whatever that is. Number of coils enclosed divided by the distance we took. Coils per, think of what unit this would be, this fraction would be. It'd be number of coils per meter. Now that we've written it in units in those terms, number of coils per meter, it's something you can get your head around. Oh, this would describe a solenoid. It's kind of like a linear density of coils. It's a linear coil density. So for example, this would have a small number of coils per meter compared to this. I've just increased the number of coils per meter. So this is a way to describe a solenoid. This would be kind of a weak solenoid with very few coils per meter. This would be a much stronger solenoid with a lot of coils per meter. And of course, this is the way we usually make them. So they're very compact. This thing here, number of coils per meter, on the equation sheet is expressed by a lowercase n, number of coils per meter. So we get B equals mu 0 lowercase n times I. This is on the equation sheet. Oddly enough, it's on the equation sheet with no explanation. Absolutely none. So you have to know what it's for. You could put this in your TI-89 if you wanted to identify what it's for, or you could just remind yourself what we just did, review it. This is for a solenoid only. It's not some general rule for magnetic field, and I've seen students make that exact mistake. They need to calculate a magnetic field, and they see a B, and they use this equation. Of course, this is only for a solenoid. You have to know what that means. This is identified as number of coils per unit length, right? I have numbers of coils per meter here. That's dependent on units, a unit system. Of course, this really means number of coils per unit length, right? So you have to know that's for a solenoid only. It is on the equation sheet. And just to give you an idea, imagine this is a metal solenoid, a wrapped wire, and we put current through it. And I want to make the magnetic field inside it bigger. What two things could I do to make the magnetic field inside it bigger? Okay. The first, of course, is to increase the current. And the second is to go like this. To increase the number of coils per meter, the linear density of the coils, that will give you a stronger magnetic field in there, which is why, to make things efficient so we don't have to use as much current or energy, we try to pack our solenoids really tightly for various things like relays and transformers and that kind of thing, the way solenoids are used. Okay? All right, so that was the solenoid. I think that was note C. And the final case where you would use Ampere's law, D, is the toroid. And I'll just introduce it, but we won't go all the way through it, and I'll leave it as an exercise for you or to look up in the book if you really want to know. The toroid has come up on AP tests, but it's pretty rare that it comes up on an AP test. And we can't do everything in class, so I don't want to take too much time on this. The toroid is what you get when you take a solenoid and wrap it around on itself, like that. This contains the magnetic field, actually makes it circular. Remember the magnetic field was straight here, you go like this. The toroid makes a circular magnetic field, and if we can, magnetic fields can be used to trap particles. We can use this to make the particles go round and round and round. If we synchronize things, we can make them go faster. So this is those cyclotron, I think it's related to those cyclotrons that can accelerate particles round and round faster and faster and faster. And think of what we would get if we sliced that. Okay? What we would get if we sliced it is something like this. Slice every coil, the ones on the inside have I coming upward at us. The ones on the outside have I going downward into the page. So each of these is a coil, right? And we've sliced it. And the magnetic field here, okay, think about the magnetic field. You'd use right-hand rule 3. Okay, so up out of the page, down in the page. Magnetic field point like that. The magnetic field line actually looks like this. It creates a circular magnetic field like that. B. And in a way, it's not that different from thinking there's like a wire inside and it's creating a circular magnetic field. And once again, if we call this distance like R, okay, we do that same thing. B, L equals mu 0 I enclosed. The B is the B. The L would be around once, right? If we decide to make this our path, and of course we would take this as the path. That way the B is always tangent to the path and the same strength everywhere. So that's nice, no need for calculus or a theta or a dot product. So that would be 2 pi R, okay? And then mu 0. Now what's the I enclosed? It's not just I, it's I times the number of coils enclosed. That will be represented with a capital N. Since this is different from a toroid, or I'm sorry, this is different from a solenoid because it wraps back on itself, we have no choice but to include all of the coils. We're not talking about the number of coils per unit length, although you could figure that out. We're just going to include all the coils, so that would be the N, the total number of coils enclosed. I'm just checking to see if I have anything else I wanted to explain before I shut off the video. Okay, and so you could solve this. I guess we're winding up doing it all anyway. 2 pi I N over R. Okay? You can also change n over r, or n over 2 pi r, n over 2 pi r to capital N over 2 pi r to little n, number of coils per unit length. So we're writing or here. Okay? And in that case, you would get mu 0 n I, which is the same thing we had for the toroid. Okay? However, this is the way I've seen it written. This is the way it's written for one of the problems in the book. This is on your equation sheet, and so you should know that's for a solenoid or a toroid. Solenoid means like a pipe. I think toroid means like a couch. Like this idea, if you put it around like this, it's like a couch, but I might be wrong about that. Okay, so that's the way you would use Ampere's law to figure out the strength of the magnetic field of a toroid.